Hello, and welcome to Patch Math, where today we are going to patch your math knowledge on simplifying rational expressions. So I just want to dive right into the backbone of rational expressions, and it is what can our denominators not be? Now notice I also put denominators plural. When you are dealing with rational expressions that have more than one denominator, we are going to, from the very beginning, be checking every single one of those denominators and what will make those denominators zero. Because if you know in mathematics, if our denominator is zero, then it violates the laws of mathematics. If we ask what makes the denominator zero, then we know what the denominator cannot be. All right, so here's what's super important. We have multiple denominators taking place, and we have to make sure we list all the excluded values for every single one of those denominators. So if you look here, I want to be using a little bit of color coding. We have this initial denominator in that first fraction. We can obviously see that right there for excluded values. So we want to make sure that we consider every single denominator and every single context in order to state our excluded values. This is something that you're going to want to do from the very beginning. Sometimes we have to do a little bit of math in order to figure out what our excluded values are. Now, if we look at that first denominator there, we can clearly see that if x were 0, that denominator would be 0. So in other words, x cannot equal 0 in this rational expression. All right, we consider that denominator as a whole. Now, we can look at this as one numerator, now that we've considered its denominator, and then look at this denominator as a whole. Now, here's what's important. This is a numerator over a denominator, or students are going to get confused because that second fraction or that denominator, I don't know why my pen's not changing. It's frustrating me. That denominator right here, there we go, finally, that denominator right here, it's going to be 0 and violate the laws of mathematics in two different places, because most importantly, if that numerator of that fraction highlighted in green there were 0, then the entire denominator as a whole would equal 0. We also have the scenario where just the denominator of that fraction, we want to look at what would make it 0, because then that would also violate the laws of violate the laws of mathematics as well. So it ends up being a little bit of a puzzle. Let's look at it one piece at a time. We know that if this entire thing were 0, then that entire denominator would be 0, violating the laws of mathematics. We know this numerator will make that denominator 0. Boy, is that like a mouthful. Now here's the thing. That numerator is represented as x squared minus 5x. To us, it's not easy to see what x would make that 0 there. All right, we don't want that to be 0. So anytime you have something like this, you want to check for a greatest common factor. We look here. Yep, automatically we have a GCF. Both of these terms, x squared is a term, negative 5x is a term, have a common multiplied part, a common factor of x. I'm bringing that x out front. What I have left over, x squared divided by x is x. Negative 5x divided by x is negative 5. So we know that numerator of this denominator. So again, that's this numerator of this denominator. It can't equal 0, or that denominator as a whole will equal 0. Now, we've got two multiplied parts, and we're wanting to consider them set equal to 0 because we don't want them to equal 0. So what will make this thing set equal to 0? Or excluded values, or what x can't be. So we have what's called the, and if you've seen some of my earlier videos, the oh my goodness, I almost forgot it. And if you've seen some of my earlier videos, the zero product property, we have a product that's set equal to 0, or we're wanting to look at it in representation of being set equal to 0. So the zero product property says if you've got two multiplied parts set equal to 0, you're going to look at possibility that one of those multiplied parts could have equaled 0, and that the other part could have also equaled 0, or they could both be equal to 0 here. That's why you were allowed to, as they'll teach in a pattern, I don't like patterns, they'll say split and set equal to 0. Well, the reason we're allowed to split and set equal to 0 is because of the zero product property. That's that why behind that how. Now you may be wondering, hey Kayla, it says not equal to. We're looking at in relation to 0. The reason we're keeping it not equal here because these are excluded values. We don't want x to be these things. Right off the bat, the first multiply part simplifies very easily. X cannot equal 0. Done. The second multiply part, it's going to take a little bit more to simplify, and that's all right if you're in algebra. At this point, you'll be noticing that this is a very early algebra skill. What do you do to one side of the equation? You do the exact same thing to the other in order to retain the original value of the equation. In this scenario, we add 5 to both sides because that's the opposite operation of how that 5, subtracting 5 there, subtracting 5 from that x, how that 5, negative 5, however you want to view it. But we're adding a negative number or subtracting 5. The opposite operation is adding 5 to both sides. So x cannot equal 5. We now have a good portion of our excluded values here. The issue is we also have one more denominator to consider because when we are dealing with rational functions, we want to ask ourselves at the very beginning, what can our denominators not be? What violates the laws of mathematics? Looking at this last denominator, you'll see x squared plus x. If that were 0, it would make the denominator of that fraction 0, violating the laws of mathematics, meaning it cannot. Meaning if it were 0, we cannot have those values in our answer. That being said, let's go ahead and look at that denominator. I'm pulling it over here so we can look at it in parts for organizational purposes. All right, so we have x squared plus x. We know that as a whole cannot equal 0. Zoom on in. First thing you want to ask yourself, even though this is a quadratic, is there a common factor, a GCF? Yes, we do have a GCF. It's a variable. Each of those terms, x squared and x, have a common factor of x that we can bring to the outside. X squared divided by x is x. X divided by x is 1. Anything divided by itself is 1 other than 0. Super important to note. And we know this product, we're looking at it in relation to 0. So the zero product property says if you have two things when multiplied and we're considering when they're equal to 0, either the first multiplied part had to have equaled 0. That's this x right here. So x had to have equaled 0. In this case, we don't want it to equal 0, so we're going to put a not equals because we're dealing with excluded values. Or the other multiplied part, I changed the wrong highlighter there, or the other multiplied part has to also equal 0. So just like the one above it, there is a little bit more math that needs to be done on this one. We're looking at x plus 1 if it can equal, and what makes it 0, because we don't want it to equal 0. Subtract 1 from each side. This cancels. Again, opposite operation on both sides of the equal sign. X cannot equal -1. Now, that was a lot of work, and we did not simplify anything. That's the frustrating part of this problem. We did not simplify anything. Now, we've done some things that's going to make our life easier to simplify, and that's not a good highlighter. Done some things to make our life easier to simplify. However, all this information is needed anytime you're dealing with rational functions. So, what did we just discover by doing all this work? That x, and I'm going to list these all over to the side. These are all of our excluded values listed out together logically. That is where they come from. And that is from that first denominator, x cannot equal 0. It was our easiest one. I'm just going to list these out. From the second denominator, this whole denominator of right through here, We also had to consider its numerator and what would make it 0, because it would make that whole denominator right here 0. So the excluded values from that. Notice we got x cannot equal 0 again. It's repeated. You don't have to list it twice. What was important, what was distinct, was this x cannot equal 5. Super, super important. From there, looking on down, we have x cannot equal 0 again from that other denominator, our third denominator. That's the denominator of the denominator. It cannot equal 0 as well. And so one of the multiplied parts when factored was 0. We don't want to list it again. But in this case, that second multiplied part, x cannot equal -1. Now, all that work, and we've not even simplified this thing, but some of that factoring might be helpful. Most importantly, this factoring and this factoring might be helpful. If you're taking notes, if you're doing this on your own paper, make a little note of that. You're going to thank yourself. Now, all of that was kind of side work. These are our excluded values. Anytime you're asked to simplify rational, because your excluded values, your wholes and your vertical asymptotes, if this were a function, now we're not looking at the function form, we're looking at the expression form, they will cancel out when you simplify your rational, or the wholes will, all right, your removable discontinuities will cancel out whenever you simplify your rational. So if you're simplifying something, we have to tell the reader or work, hey, there were these excluded values that are meaningful to our final result, but got canceled out from the original. Now you may be looking at this. I have so many fractions happening here. How am I going to simplify it? I'm going to take some of my shading off, and I want you to look at just the top blue parentheses and the bottom parentheses. Between those two parentheses, we have a middle fraction bar. So we have a numerator divided by a denominator. All right. We also have this rule that says if one of our numerators is a fraction and that's divided by another fraction, we can keep the first fraction as it is. We can change the operation. So maybe knowing where this is going, we can change the middle operation between the two fractions from division to multiplication. And if we do that, we must flip a super important part, the second fraction in the denominator. This is called keep, change, flip, and it's kind of competing there with that. Let me put it there. All right. So we keep that first fraction. X squared minus 4x minus 5 all over x. We are going to change that middle operation from division to multiplication. I like to use parentheses if you know me. All right, then we must flip. That means take the denominator to the numerator and the numerator denominator for the second fraction. And I said that in one big blur. All right, so that denominator of x squared plus x now becomes the numerator. And then the x squared minus 5x becomes our denominator. Keep, change, flip. Now, this is where some of your factoring may come in handy. You'll notice we've got multiplication and division happening between our main parts there, but none of our parts are going to cancel out. That tells us that we want to factor parts of this to see if anything will cancel if we're choosing to simplify. If we look at this first numerator, that is a quadratic. Quadratics, you do want to check for a GCF. We have an A, that's a leading coefficient of 1 here, so we don't have a GCF. But what we can do is called the AC method. If you're at this point, you should be able to do it in your head for rational functions. I can imagine having to do AC method off to the side in addition to all the work we've just done. So in this case, we're looking at the factors of -5 that add up to -4. We are dealing with x minus 5, x plus 1. If you are ever confused, simply FOIL that out. First, outer, inner, last. If you get x squared minus 4x minus 5 back out, then you know you got it correct. In this case, we do. -5 times 1 is negative 5. 1x minus 5x is negative 4x. Going to go ahead and leave that denominator as it is. Looking on over here, this is where some of our earlier factoring is going to come in handy. Notice you already factored this down here. Use it. Notice also I wrote the wrong sign here. Glad that happened. Copy over error is one of our most notable types of error. This is not equation. This is an expression that is multiplication between the two parts. In this case, x squared plus x, its factored form is x times x plus 1. My x's are looking strange there. X plus 1. All right, this denominator, we did already factor it over here in order to find our excluded values. That is the x times the x minus 5. Don't redo the work. It's one of the good reasons of doing your work over to the side. Now that we have all of these factors, you'll notice, yes, we have addition and subtraction taking place inside of parentheses. That's not what we care about. We are asking ourselves, between each of these parentheses are the only operations multiplication, as I've shown there, and division, as I've shown here. And so the answer is yes. Why does that matter? Because in PEMDAS, when we are dealing with order of operations, multiplication and division are created equally in terms of order for simplifying. If between all of our parts, we just have multiplication and division, we can choose to cancel on division before we choose to multiply. In other words, we undid some of the multiplication that had already been done by factoring, so that way we could choose to cancel before we multiply. That's the whole idea here. In other words, we cannot cancel across addition and subtraction, and it's super important. You've got to make sure any addition or subtraction is within the parentheses, the factors being canceled, not between the parts being canceled. Super important. In the scenario, you'll see that we have an x minus 5 and an x minus 5 that sync up. Those do cancel out. You'll also see that we have these x's right here. They also cancel out. You could have potentially chose to cancel with this other x. That is up to you. Now that we look here, you'll see that we have the x plus 1 and the x plus 1 in the numerator. There is no x plus 1 in the denominator for them to cancel out. They just come together as they are, x plus 1. You can write that as x plus 1 squared, like so, since they are the same factor, the same binomial square, over x. If you choose to simplify this out further, you could look at that as the x plus 1 times the x plus 1. Choose to FOIL it. You do have some teachers who are going to ask you to do that, so I'm going to go ahead and look at that form. You end up getting x squared, that's the x times the x. Then you get plus x, that gives you the 2x. That's this plus x, first outer, and I did that wrong, plus x, inner, and then last. So then we get plus 1, multiply those together, you get positive 1. That is your numerator. This is your denominator. Looking at that, the only way we could possibly have anything that canceled is if that would be helpful, is if there was a GCF of x in the numerator. In this scenario, we do not have a GCF of x in the numerator, so we are done. That quadratic isn't factorable to anything that's going to cancel with that denominator, and that's how we know we're done. Now, what's super important, whenever you list this final answer, you must make sure you list the excluded values along with it. And you'll notice x cannot equal 0. Its information got retained in this expression, all right? However, x cannot equal 5 and x cannot equal negative 1. Those factors canceled. However, if at in the beginning, if those areas, x had been those numbers, it would have made a denominator in one of our original fractions 0, violating the laws of mathematics. So the fact that they were present in the beginning means they do have to be accounted for in our final answer. And there you have it. A very, very exhaustive rational expression simplification, while also considering all of the excluded values that would have caused this expression to have 0 in any of its denominators. All right. Thank you so much for your time.